One of the key differences between the LQR controller and the PID controller that most of the other groups use is that it actually takes feedback from all four states. And by states, I mean the angle, angular velocity, the position of the wheel, and the velocity of the robot as it goes forward and backwards. And then you have a weighting matrix that weights the importance of those states. So, for example, like it knows that the angle is the most important. So while it's keeping the angle balanced, it's going to try to drive the velocity of the wheels down to zero as well. It's keeping it from just going indefinitely one way or the other, just keep itself up. But we actually ended up getting rid of the gain on the position as we went on to get rid of some of the oscillation. And so it's actually more of a lead compensator PID controller now than an LQR.
We went the really simplistic design, and one of the reasons we did that was just really easy to construct and really simple, so we didn't have to worry about rough hardware and anything like that being near the electronics. And as time went on, like a few key changes we made was like the accelerometer we had on the bottom, really close to the motors, and it was getting some vibration from that, so we moved it up towards the center of gravity and actually put tape underneath it to keep it really stable, so it was not shaking at all as motors or screws or anything let it, so it gave us much better readings from that. The IR sensor on there is also a small, sleek design.
Also, our main sensor is the 3-axis gyroscope accelerometer. And so one of the problems, well, 3-axis each. And one of the problems with gyroscope is that over time, the value drifts. And then the accelerometer is very sensitive to motion beyond just gravity, obviously. It comes in any acceleration. So we use a complementary filter, and it kind of brings out the best of both of those sensors. So when it's filtered, you kind of get rid of the drift from the gyroscope, and you get rid of a lot of the noise from the accelerometer, so you get really accurate angle reading. The motors we're using are Lily motors with 50-to-1 gear ratio, and what was that? It gives
1.2 meters of torque and 200
RPMs, which we feel like obviously would be ample enough speed and torque to keep the robot upright and balanced. And it's being driven by a dual motor driver. So one integrated, one PCB that 12 volts goes into, and then we also feed a PWM from the TIVA, and that controls the apparent voltage to the motors. And so as the robot needs more voltage to the motors to balance, the PWMs change and more voltage is supplied. Correct. Keep it upright.